came just after the previous very nice talk, because I'm also going to talk a little bit about sensing and metrology. And so in the previous talk, you have already heard about why it might be interesting to use. I can do it on my. I know it doesn't work at all. No, it's the computer which is.
But it's frozen.
Oh, yeah. One second. Okay. I think even now it would work. Okay, so in the previous talk you already heard why we are interested in using quantum sensor in order to measure with very high sensitivity. And the usual motivation is that we can use large entangled systems to achieve sensitivity which are beyond what is possible with classical sensors. I think that there are also two others reasons why one might be interested in using quantum sensor, and in particular why this is relevant. Does this work? Yes. Why this is relevant for hybrid systems. And one of the reasons is that what one can do is really to use one quantum system in order to measure a second quantum system. So in this sense, what we're really doing is to try to control and detect a hybrid quantum system, which we call one part the sensor and the other our target system. And the other reason why it might be interesting to try to use a hybrid system as quantum sensor is that we might be able to build some small quantum information processor, which might allow us to run some small algorithm, which would improve the sensing task itself. For example, instead of just being able to sense a single parameter, we might be able to sense some time dependence of the parameter, or maybe even identify fully the Hamiltonian of the system. And so I think that for this reason, it is very much relevant to try to talk about sensing in the context of a hybrid system. And here I have two examples for this idea of using one quantum system to detect other quantum systems, but I think that the previous talk actually presented so many more examples. But these two examples come from my own field, so R&D centers. And so there has been some recent work in which people have used a single spin to try to detect some interesting many-body quantum dynamics. In this case, is related to magnetism, in order to have some first ideas about how, for example, spin waves behave in ferromagnetic materials. But more generally, what one could try to do is to unravel very sort of exoteric and complex state of matter, like, for example, classes, etc., using these very localized quantum sensor. Another example, still within the center, which is sort of related to this idea of trying to use a small quantum processor, sometimes even a hybrid quantum processor, in order to inform more information about the target system that we are interested in using. And again, within the center, where what people in the machine learning group have done is to use not only the anti-center as the sensor, but some other electronic spins which appear naturally on the surface of the diamond, in order to get better information about the presence of nuclear spin on the surface of the diamond itself. So if you want to do this intermediate, use this electronic spin as transducer in order to gather more information about the third quantum system on the surface. So these are some examples, and I'd like to sort of expand a little bit more on that. But before doing that, I just want to give you a very brief review of what we mean by quantum metrology, and in particular some the precise task, which is parameter estimation and some limit of it. So one of the simplest ways in which you can sort of think about parameter estimation is to consider it as just a Ramsey scheme, or if you are from a different community, from an interferometric scheme. So the idea is that there is some parameter that you are interested in measuring. For example, here is a magnetic field, B, which is connected to your sensor of choice. And well, for me, by now, you know that my system of choice are spins. So I have some Giro-Mann integration, which give my Langmuir frequency. But this is quite general, could have any other system coupled to some external classical parameter. And what you would like to do is to infer the value of this external parameter B. So one thing that you can do is, for example, to put your spin in a transverse plane and let it process under the action of this external parameter. Or more generally, you observe the dynamics under the action of your true level system of choice under the action of the external parameter. And then what you're able to do is to measure this parameter. And of course, you always will have some error in the estimate. And if you wanted the real task is to try to minimize this error in order to have the best possible estimate of the parameter itself. So there are some fundamental limits in how well you can estimate. So what is the fundamental bound of this error? If one wants to be precise, one can, for example, define the feature information associated with the parameter. But for this type of true level systems, actually what you have is something which is much simpler. So you can, another way of looking at this is if you want in a quantum information language, you create some superposition of your true level system with some gate, for example, a Hadamard gate. And then you will have some phase gate, in this case, under the action of this external Hamiltonian, and then you do the emulation. And then the uncertainty in the parameter is just given by the uncertainty in the signal itself, so the error in your measurement, divided by how the signal varies with the parameter of choice. So this is what this quantum Kramer-Rao bound reduces to when you just have a two-level system with no noise and nothing happening to it. But of course, this relationship is very intuitive, and so it will also hold very general terms for a more complex system. However, one has to be a bit more careful when one starts introducing some more complication into the system. So how can one sort of improve onto this limit? Well, the first thing that you can do is to say, instead of just using one single qubit, you can use more than one in order to be able to improve the resolution. And again, with this, if you want to just like almost a classical scheme, you just summing up all the signal. And so for short noise limited sensitivity, you will have that this error in the estimate of your parameter just goes down as 1 over the square root of the number of the probes that you're actually using. So it's really working.
It works.
It works, huh? Okay, so I don't have to go back and forth. So the second way in which you can improve, again, your sensitivity, just to repeat your experiment many times. This is what we do all the time in the lab. So if you repeat your experiment, let's say, m times, then of course it will take you a total time, capital T, which is m times the time that it takes you to run the experiment only once. And so the sensitivity, again, this error in your estimate will go down at the square root of this total time. So again, these are very classical ways of improving your sensitivity, but of course you can also try to do better by using, again, quantum mechanics. And so one, there are, if you want, like 2 strategies that one can try to go to adopt in order to go beyond the standard quantum limit. And the first one is the one which is the most common described for quantum metrology, because it's really inherently quantum mechanical. And it is to prepare an entangled state. So you can, instead of preparing just a simple superposition of each one of your sensor, you prepare a superposition in an entangled state of all your sensor, for example, a cut state, and then you measure again this phase. Now the estimate will go down as 1 over n, so 1 over the number of your probes, instead of 1 over square root of n as it was for the classical case. So you have a square root of n improvement in your sensitivity. The second way of improving things is, if you want, a bit like cheating. So instead of repeating your experiment many times, you could try just to repeat the experiment with one doing measurement in between. And so you just measure for a longer time. And also in this case, what you gain is a factor of 1 over square root of the total time of your experiment. And so it's also in some sense a quantum limit, although every time that I present this, people think that I'm maybe cheating, but if you want, it's another way of proving things. And while people are usually sort of concerned about saying that entangled states are challenging, difficult to prepare, etc., both these strategies have benefits. They improve the sensitivity, but they also have, of course, challenges and drawbacks. So for entangled state, this is the challenge that most of the people focus on, but I think that there is also a second challenge, which is to say if you have a large system entangled, with which you're trying to measure some external parameter, you also should make sure that the parameter that you're trying to measure is homogeneous over the extent of your large quantum system, otherwise you will not reach this quantum limit. This is very similar to the limitation in the second strategy, which is to sort of measure for longer, because also the interrogation time is always going to be limited, so you cannot really measure for a very long time t. You can measure your sort of limited by the coherence time of your sensor itself. And similarly, also your parameter might have some time-dependent variation, and so this is a second limitation which doesn't allow you to go and measure for too long time. So this is, if you want, a very short introduction to what you can do in order to do this task of parameter estimation. But what we are interested now is instead to sense a quantum system, and this might be even more challenging because, for example, even a quantum system might have some finite coherence time, and so this is another limitation. Instead of having finite spatial homogeneities and parameter variation, you also have to take into account that your quantum system might not survive for as long as your quantum sensor. So what are examples of this task of sensing quantum system, which is, I say, it's quite nicely falling into this idea of using hybrid quantum system. So we have heard in the previous lecture and also in many other lectures that one can use, for example, a spin sensor to measure the position of a quantum mechanical oscillator. And so coupling these two different quantum systems in order to measure each other. Another nice example was used, for example, by Serge Roche in a series of various experiments. So this is from, I think, the first one published, in which he used Rydberg atoms created and rotated in this force cavity in order to detect in a non-demolition way the number of photons which were inside this cavity. So depending on the number of photons, these Rydberg atoms were acquiring a phase shift which was directly proportional to the number of photons in the cavity itself. And so without really destroying the electromagnetic field inside the cavity, we were able to measure how many photons were inside the cavity. And so this is, I think it's a nice example which shows that really using a quantum system, the Rydberg atom, to measure a second quantum system, the finite number of photons in the cavity, allows you to do something which is very difficult with classical means, which is to say that you can do a measurement without really destroying the quantum system. So this is the idea of quantum non-demolition measurement, and I think it's a very nice example of using this freedom given by a hybrid system to infer more information about a quantum system. So another example is sort of related to my second lecture. So I talked a lot about how we can use, for example, a spin chain. So here these circles are spins, in order to transfer information down a chain of spins. And one of the questions that I got was, do you really need to know what are the characteristics of this spin chain in order to be able to achieve perfect information transfer? So the answer is, in general, no, if you're clever enough about which tricks you use in order to achieve this perfect transfer. So one of the ideas was to use this weak coupling regime coupled with resonance to a collective mode to achieve this perfect transfer. But on the flip side, one could also use the internal evolution of these spin chains itself in order to infer what is its Hamiltonian. In particular, here what they showed was that it was possible with just controlling this for spin and just measuring this for spin to infer what were the coupling strength among the spins. So here we were coupling strength different one from the other. And so you do not need to have access to the full quantum system. You can just use one single quantum sensor to infer the full structure of your system. And this is true over very broad, if you want, assumptions, so you just need not to have too much symmetry in the system itself.
But does that get, is that to a normally hardened system size or exponentially hardened system size?
That is a good question. I think that it was just polynomially hard, because we claimed it was, yeah, so it was like just linear in the number of spin-offs. But of course, the assumption was that they knew what was the type of Hamiltonian. So that they assumed it was an Heisenberg type of Hamiltonian, and they only want to figure out what are the n couplings among the spins. And it was nearest neighbor coupling only.
So it's not in general.
So it's not a general structure. Yeah, it's not a general. So I think that like, I don't remember the exact detail. I think that they probably claim it like for, they worked it out also for general like quadratic Hamiltonian, so again, just two body terms, a bit more general than just the Heisenberg Hamiltonian. But it's not, I mean, of course, like if you have a full Hamiltonian with like 3 full body terms, then it's not going to be polynomial. But for if you restrict to things which are quite natural, like two body Hamiltonians, then yes, it was efficient. Yeah. So more generally, there has been some work recently in so-called Hamiltonian identification for more general systems. And the idea is again to try to find what are conditions under which you have the ability to measure, or if you want to reveal what is the Hamiltonian structure of your system by controlling either the whole system or possibly just a subpart of it. And there is one recent paper which has some nice algorithm with which they are able to solve this problem. But in this case, we were assuming to have full accessibility, full measurability of all the system. Again, because I'm more interested in spins, I will spend some time now talking about another example, which is to try to use a spin sensor in order to detect the presence and position, and so reconstruct, for example, the structure of a particular spin system using one electronic spin sensor. And the idea here is that we can nowadays really achieve spin sensor. And when I say spin sensor, I typically think about the MB center, but if you can come up with some better defects, possibly not even in diamond, but in cheaper materials, that would be nice. But for the moment, we are focusing mostly on this MB center, and it's possible to create them very close to the surface. So right now, one can create with very low energy implantation at about 2-3 nanometer below the surface of diamond, and still have coherence property which are not too bad. So just still like digital times over 10-50 microseconds. And so the hope is that then it would be possible to measure individual nuclear spin outside the diamond itself. So there has been already some results along these lines, but I think that what it would be really interesting is not only to show that you can measure a single nuclear spin, but you can do so even if this nuclear spin is inside a very complex molecules, where the density of the nuclear spin is very high. So even if you are able, for example, to sense an individual spin, because the presence of all the other spin, the signal is sort of masked, so it's difficult to really say you measure a single spin and this is its exact position. So the problem sort of shifts from just the problem of sensitivity, being able to detect the signal, to a problem of frequency or spatial resolution. The two things are, of course, connected because the frequency of each spin depends on their position inside the biomolecule. So why one would be interested in sort of tackling this type of problem? Well, the idea is that what we would like to really try to detect are single molecules in their natural environment. So typically people detect and reconstruct a structure of proteins or biomolecules by different means. So one is X-ray crystallography. But of course you need to synthesize the molecule in sizable quantity and then crystallize them. And there are some type of molecules, for example, membrane proteins, which are very difficult to crystallize, especially in amounts which are large enough to be amenable to X-ray crystallography. Also, it's not completely clear if proteins which are crystallized have exactly the same properties than proteins which are in their natural environment, even like a liquid environment. And so it would be quite nice if one would be able to really sort of look at proteins, individual proteins. So if you cannot engineer many of them, you can still look at them and in their natural environment. And also maybe look at their dynamics, how they bind to different ligands, etc., which is really at the basis of how we can develop new drugs. And as I say, the challenge is really to try to find a single nuclear spin position, even if they're embedded in a very high density set. So what are strategies that people have until now adopted in trying to sort of solve this problem? So this sort of brings us back from to my first lecture, in which I showed you that if you have an electronic spin coupled to a nuclear spin, you can control the evolution of the nuclear spin by just flipping the state of the electronic spin itself. So the idea is that, of course, in the two different manifolds of the electronic spin, the nuclear spin is effectively a different Hamiltonian, because you have coupling of the electronic spin to the nuclear spin, which adds to its internal Hamiltonian. And so if I sort of concatenate the evolution under the two different Hamiltonian in the electronic spin manifold, I will possibly engineer a controlled evolution. So how does this work? Well, for example, I start with my nuclear spin in this state, and then I apply these pi forces on the electronic spin. And so I will sort of follow some particular trajectory which brings the nuclear spin to some new state here. But now what happens if I, instead of having my electronic spin in the mass equal 0 state, I have the electronic spin in the mass equal 1 state? Well, the nuclear spin will start from the same place. I am applying the pi forces at the same time, but of course the nuclear spin will follow a different trajectory, because it will evolve under different Hamiltonian during different time periods. And so the final state of the nuclear spin is different, and if I create a superposition of my electronic spin, this superposition will in general decay, because what I have is a destructive interference between two different parts of the electronic spin itself. So I can really use this same idea of this controlled rotation of the nuclear spin, now not for controlling the nuclear spin, but in order to detect what is its coupling to the electronic spin itself. So I can really measure this interference effect between the two paths in order to sort of get information about what is the coupling of my quantum sensor or quantum actuator to the target nuclear spin. So this is what people have been used in order to detect this nuclear spin. So the method is with dynamics under hypothesis, and there are two ways, if you want, of looking at it. So one is a more classical way. So you consider your spin, and very often they're a small ensemble of nuclear spin, as just classical magnetic dipole. They have their own intrinsic energy given by the Larmor frequency, and so they will process this particular frequency in time. Then what you do is a pulse sequence in which you have these pi pulses here. And of course what we saw was that when you have these type of pi pulses, if you have a static field, these get cancelled out because the sign during this time period is the opposite of the field during the second time period. But now what I have is this classical Larmor oscillation of my magnetic dipole associated with the nuclear spin. And if I select the timing of my pulses so that they are synchronous with this oscillation of this oscillating magnetic field given by the nuclear spin, now I have a constructive interference, if you want, the phase adds up in a constructive way, and so my sensor acquires a total phase which is non-zero. So what I will see is that when I match this condition, so that I have this synchronous oscillation with the timing of my pulse sequence, I will have a decay of my coherence of my sensor because it's acquiring the phase due to all the speed. So it is, if you want, a very classical point of view, and it's very good to get an intuition of what is going on. But of course, at some point you will fall down because what we are observing are not classical magnetic dipoles. So it is good if you are measuring an ensemble of spins, but if you really want to try to go down to the single spin limit in which you are detecting a single spin, then maybe a quantum point of view will be a bit better suited to really see what is going on. And we can also understand that in a quantum way. And this comes back to this idea that you will sort of achieve different dynamics depending on what is the state of your quantum sensor itself. So what I'm plotting here is the evolution in the Bloch sphere of a nuclear spin. Either if the electronic spin starts in the mass equal 0 or in the mass equal 1 state, for two different spins. So this is a spin for which I'm sort of matching this condition, that its internal frequency is sort of matched with the timing of my pulse sequence. While the spin here, it's not on resonance, meaning that it oscillates at a frequency which is not very well matched with the pulse sequence itself. So what happened? Here is the initial state, and then I start applying pulses. And so in this case, what I will get is that the two manifold have a different evolution. While in this case, the two manifold, the evolution is still a bit different. Of course, something is still happening, but it's not all that much different. So in this case, I have at the final point, the state of my nuclear spin is very different, depending what was the initial state of my electronic spin. While in this case, the spin state is very close to each other, no matter what was the initial state of my electronic spin. So in this case, if I look at the electronic spin, I will see a decay of its coherence, or a change also in its state, because of the nuclear spin to which it is interacting as a bond, while in this case, the electronic spin will still be more or less in its initial state. So what exactly can one see? Well, again, if one tries to measure ensemble spins, what you can see is really sort of a behavior which is very similar to what you would have if you had just a classical magnetic field oscillating at a given frequency. So here what I'm plotting is the result coming from two different NVs. This is from the Lukin and Wordsworth group. So these were two different NV centers very close to the surface. And what we were looking at was actually at a special oil for the oil immersion lens, which contained not only protons but also fluorine. I think it's called Hamlin oil. And so what you see is two different peaks here. So the blue is for one NV and the red is for the other NV. And these two peaks correspond to the frequency of these two different spin species, either proton or fluorine 19, at the magnetic field that we were using. I don't remember how much it was, on the order of 1200 Gauss. And so what you see is like this broad peak corresponding to the presence of an ensemble of nuclear spins. So this is quite nice, so we were able to measure the presence of this nuclear spin outside the diamond itself. But of course, we do not know how many spin I have here. So I can estimate, given the density of the oil itself. But it's not that I can really say, okay, I'm measuring a single individual nuclear spin. And it's not so much a problem that the nuclear spin, and I cannot really distinguish one from the other. And the fact that it's not really a problem of, if you want, of sensitivity, it sort of showed that from the fact that if you do have a nuclear spin system which is much more sparse than this oil, you can actually see individual nuclear spin. So this is, has been shown also for isolated protons absorbed on the surface of the diamond, for sample with silicon-29 silica in the Ooms group. But I think that like a nice example, a nice picture is this one, which comes from instead carbon-14 intrinsic to the diamond itself. So what you can see here is a signal which is very similar to the one which I show here. So basically this is the same type of plot. So you measure how much contrast you have left over when you are applying this sequence of pulses. And here is plotted in terms of the time, so for longer and longer time. And the short time, you still see just a broad dip, if you want, which tells you, yes, there were some nuclear spin around your epicenter, but you don't have enough spatial resolution to detect. But then when you go for longer and longer time, you start seeing a very nice structure here, in which you have more than one peak. And in this particular case, which was coming from 5 different nuclear spin, which were around this particular epicenter, randomly put because they're just like 1% natural abundance. And from this structure, we were able to reconstruct where these nuclear spin were actually being into the sample. However, this is possible because we were only 5 spin and not so close. So because you have this 1% abundance, nuclear spin in diamond are not so close to each other. If you instead want to do the same thing for this type of sample, it's not a problem of going for much longer time and having much longer coherence time. It's still going to be almost impossible because the spin are so dense that one limitation, for example, is the coupling among the spin themselves. So that would sort of broaden your line itself. So what can we do? Is there some other strategy that one can try to adopt? So another strategy that we have explored is instead of trying to measure, if you want, the presence of this nuclear spin by the fact that they sort of reduce the coherence time of your sensor, what we did was to try to sense the spin by looking at the fact that the presence, the coupling of the spin, of the sensor spin to the nuclear spin also reduced the polarization of the electronic spin itself. So typically we will have again our epicenter, and we can polarize it optically. And this polarization then can be exchanged with the rest of the nuclear spin system as long as we do some resonant driving. And we'll explain a bit better what I mean by that. And again, this might not give you enough spatial resolution. But by using the scheme, we can sort of bring in some extra tricks, which really allows us to improve the spatial resolution of the detection method itself. So the first thing is that what we can do is to say that the epicenter itself not only can be used in order to detect the spin, so as a sensor, but it's also creating a magnetic field gradient at the location where my spin system is. So here, for example, I'm plotting the rest of the protein in just its normal color, but for the spin which are close by, I plot them in terms of the frequency shift, which is induced by the presence of this epicenter close to the surface. In this case, it was about 2 nanometer below the surface of the diamond. And here, similarly, what I'm plotting is this color code is the effective field that the hyperfine and the color coupling of the epicenter creates at each one of the location outside the diamond. And we can use that to, again, shift the resonance frequency of this nuclear spin and hope to detect them with better spatial resolution. So this is quite nice, but of course, we cannot create a field gradient for a very long time because the epicenter will, in the end, decay down. So what we do is to exploit the fact that actually we have a second nuclear spin, so we really use this small hybrid system and use this nuclear spin as a memory in order to extend the coherence time for much longer. so that we can really sort of use some sort of memory intrinsic to the MV center itself, and combine this with this field gradient to achieve a better spatial resolution. So in the end, what we want to do is really to sort of achieve three different goals. So the idea is that, let's say that I have two nuclear spins which are outside my diamond. Okay. Because of their interaction with the MV center, there is two different effects. So one is a shift in the resonance frequency, which I will call A. And this is just due to the longitudinal part of the coupling between the MV center and the spin themselves. And then there is also a transverse coupling, which I call B, which is sort of responsible for flipping the nuclear spin. So in principle, when I have just these spins, if they're very close, their different resonance shifts are very close to each other. And so it's difficult to really distinguish them. What I can do is to add a gradient, and that will sort of put the two resonance frequencies of the nuclear spin more far away. And so this gradient, as I say, could be created by the nuclear spin, by the MV center itself, or for example by these electronic spin which are on the surface, or by some permanent magnet, or any other name that you can think. However, this is still often not enough to really distinguish the two spins. So what we can do is to try to use a control scheme, so that instead of being coupled to both of these two spins, now I'm only coupled to one of the two spins. So this can be used, this can be achieved by using control to map the difference in frequency into a filtering action which cancels out this coupling here. And then the third thing that I would like to do is also to eliminate the coupling between these spins, which is my target, to the other spins. And that will reduce the intrinsic line width. And so I will be able to measure again with better frequency resolution, which then translates in a better spatial resolution. So how can we achieve this? So what we did was to come up with a rather complicated control sequence. But I'll try to walk you through it so that it's easier to understand. So the first part is very easy. So we just initialize the sensor with a laser pulse. So this is what Greg explained to you, what I reviewed in the first lecture. So you can polarize the MV center by shining green light because of the nice combination of its energy levels, which allows you to really polarize into the zero spin. In the same way, what you can do is to use the nuclear spin and use some control pulses in order to map this polarization onto the polarization of the nuclear spin itself. So this can be done naturally if you are at one of the alveolar crossing between the NV and the nuclear spin, or just by using some pulse control, so like you do some kind of swap gain. At the end of the day, you also want to again measure your NV center. So again,
now you use N15 instead of N14, or it doesn't really matter.
It doesn't really matter. So this mapping, like with pulses, is slightly easier with the N15. Because it's been 1 hour, so it's slightly easier. But
there's not,
it's, yeah. So it's not fundamental. I think that like I use N15 because it's slightly shorter in time, so it gives the overall scheme becomes a bit faster. Okay, so yeah, at the end of the day, you still want to measure the NV. And one thing that you could do is actually to use the N15 in order to improve this final measurement by doing some bigger reduction. Here. And then in between, there are basically two fundamental steps. So one is so-called spin lock, which achieves polarization transfer. And we'll show you in a second how that happens. And the second one is a time during which we have this light gradient. In this case, just to have a simpler sequence, because this was already complicated. What we were thinking of doing was just to use the NB as the source of the gradient. In order to be able to really use this gradient for a long time, before applying it, what we do is to swap the state between the NB and the nuclear spin, which acts as a memory, so that we can store the state of the electronic spin onto the nuclear spin, which has coherence time of the order of millisecond, and that allows us to apply this gradient for a long time. And then we swap back the state, and we can repeat this overall scheme for some time. We also think of applying some control onto the nuclear spin. And these are so-called homonuclear decoupling sequences, which are very well known in the tradition of nuclear magnetic resonance. They have typically very weird names, such as Wabuka or MRF. They are typically just the initials of the people who invented them. But I mean, NMR has a tradition of giving very, very weird names to sequences. So you have things also like the Dante sequence or the Concertino sequence. So you need to have a very wide imagination in order to survive in the field of NMR. But for homonuclear decoupling, for example, you can just apply some hydrogen pulses along some different axes, and what you achieve is to cancel out the dipole-dipole coupling among the spin themselves. And this helps in sort of achieving this narrower intrinsic landing. So why, yes?
So if you want to do this decoupling, how much do you have to know about the two spins if you want to?
Oh, no, you don't need, I mean, so you need to know what is the average, let's say, coupling strength, because you want to pulse faster than that.
And you need to know their distance?
So
it's the same thing, I guess.
Yeah, so it's the same thing. So you need to know that more or less nuclear spin and the protein will be, I don't know, something like some Armstrong and part one from the other. So the coupling strength is on the order of low kilohertz to 100 hertz, and so you need to pulse faster than that. But you do not need to know anything else.
Oh.
So yeah, so like the idea is quite simple in the way. So you have your fantastic polar Newtonian here, which is already very nice. And of course, this will have like Dij and sum over all the points. So typical sequences, what they do is to periodically rotate this into another Hamiltonian, which looks like sigma x, sigma x. So this part, so you're applying collective pulses. So this part does not rotate because it's invariant under a collective rotation. So what you do is you're only rotating this part here. So you will have sigma x, sigma x, where you will have something like sigma y, sigma y. So on average, this I will have again here is a term which looks like sigma dot sigma, which cancel out with this second part here. So this is like very basic frequency. So you don't really need to know what are these coupling here, because it's cancelled out in any case. And again, then you can use higher order representation of the sequence, etc., to achieve this not only to this fourth order approximation, but also to higher order approximation. Okay, so this is the overall sequence, but let's say I need to explain a bit better what are these two fundamental steps which we are using. So the first step is with spin lock. So again, this is NMR jargon. The idea is that what you're doing is to lock your spin along your driving direction by applying a strong driving after you have rotated your spin in that direction itself. That's, again, NMR jargon, but if you're more into the AMO community, you can very easily understand the concept of rest spaces. So what happens? So here I have my energy levels of the electronic spin. These are on the order of gigahertz, okay, for the energy center and for typical magnetic field. And here is the energy level of my nuclear spin. These are on the order of megahertz for the small magnetic field that we are considering, or maybe even lower if you don't apply a large magnetic field. So what I'm trying to have is that this transverse coupling between the two should try to exchange energy between these two systems. which is the same as exchanger with polarization. But of course, this will never happen because the two energies are so far apart that this flip-flopping is very much forbidden. So, well, how can I achieve then this polarization exchange between the two? Any idea? I have to drive it, exactly. So what I can do is, for example, to drive the electronic spin, this is the easiest scheme in this case. I drive the electronic spin with a Rabi frequency, which is now on the order of megahertz. And now this becomes on resonance with the nuclear spin. And so now this transverse coupling is really able to allow this energy exchange between the two systems. Yeah, there was something in there which is not appearing. So the message, I remember what is in there. The message is that one, we can achieve this resonance coupling, but that's not the only thing. What you're also doing is that because you are continuously driving your electronic spin, you are also decoupling it to any other type of noise, which doesn't have the same energy here. So you achieve two things. You are putting it in resonance contact with your target spin, and at the same time increasing its coherence time. So what you achieve is so-called T1 rho coherence time, which was here, which is on the order of milliseconds. So this is, if you want, is the equivalent of the relaxation time, but now in this rotating frame, which you have induced by this driving. Let me see if I just to make it.
Here.
A nice thing is that because you are driving in a continuous way, it's still easy to apply the same time with a homonuclear decoupling sequence. This is not so when you apply this hypothesis for detection under these hypothesis, because what you would like to do would be to apply the coupling sequences here for your nuclear spin on a time scale which is faster than the hypothesis is applied to your sensor. But typically your sensor decays much faster than your nuclear spin, and pulses on the nuclear spin, even if you have some very good amplifier, will take on the order of 1-2 microseconds, which is too long to embed the decoupling sequence inside the decoupling sequence for the electronic spin. Instead, because here you have just some continuous driving, then you can just do the two at the same time, and so it really allows you to achieve this intrinsic, very narrow line width. So the second thing that we want to do is to achieve this filter in which I only keep the coupling to the target spin which I want to measure. So the idea is the following. So I've done this resonant driving. So now my whole Hamiltonian in an appropriate rotating frame will only be given by this exchange Hamiltonian between my electronic spin S and my nuclear spin I. So what happens now is that if I add a gradient, this Hamiltonian will sort of add a phase factor which modulates each one of the nuclear spins depending on the position of the spin itself. So now instead of having this exchange Hamiltonian, I have this modulated exchange Hamiltonian. Should probably add a T somewhere. And so how can I exploit this? Well, what I can do is to alternate between the time during which I have this polarization exchange and the time during which I have this gradient on. And by combining them, I will have it on average. Each one of my interaction will be modulated by a factor, which turns out to be a nice filter function, which depends on the frequency of the spin itself. So in this way, this coupling will survive only for the spin which are on resonance with the particular magnetic field which I'm applying. And so what I can really do is that this term here will only survive for spins which are in a very narrow frequency window, so in a very narrow spatial window away from the nucleus spin, away from the MD center. And so this really achieves a much narrower line width than if I do rely on this resonant exchange between the two. So with this, what we can do then is to try to simulate really what would happen if we had my MD center, which is somewhere around here, close by to a particular binding site of a protein. So we just choose, I have to say, almost a random protein. We try several different proteins that were similar. So this one was particularly visually appealing. So the one thing is that you can see that this pin here would have been much more strongly coupled to the MD center because we are more protruding, but we were not really anything interesting. So what is interesting is to try to measure particularly binding site of the protein to which a possible drug would be able to attach. So in this particular case, this protein is responsible for things varying from Alzheimer's to AIDS. This particular binding site is the target of the protein of the drug for Alzheimer's. So it seems sort of interesting to try to see if with the MD center we would be able to measure. So what do we obtain? So again, what we do is this polarization leakage. So every time that I'm on resonance with one particular spin, the polarization leaks out from the MD center and observe less photons which are emitted because I go to one with plus or minus 1 state. And so here is the type of spectrum that I would be able to observe. Again, on the x-axis, basically what I see is this resonant frequency shift, which is due to the presence of the MD center itself.
Is this an experiment or is it
No,
simulation?
it's a simulation. Yeah. Okay. So we are working with this experiment. It's not as easy.
I'm sure.
So the width of each one of these peaks depends instead on the coupling strength to the MD center itself. And of course, there are places where two spins are very close to each other, so we cannot really solve them, even with this. But in other cases, then we can resolve individual spins. So out of this type of spectrum, what we really achieve is 2 parameters for each one of the spins which are present. And so in principle, given these 2 spins, given these 2 parameters, I could say, okay, I have an MD center here, and then spin number 1 should be here, and spin number 2 should be standing in this other position. However, this is not really enough to fully say where the spins are. And the problem is that the dipolar coupling between the electronic spin and the nuclear spin has an intrinsic symmetry. And so actually, based on these 2 parameters, I can only say that these 2 spins are in somewhere around this core here. And so I cannot really say what their position is. However, there is a third advantage of the polarization leakage method. So the first one was that, I was able to use this leakage and at the same time increase the coherence time of the MD center. The second advantage was that I was able to do is the coupling of the spins at the same time. But then I also have a third advantage is that now what I've done is actually to polarize selectively one of these spins. And now I can use these spins themselves as probes of their environment. So these spins, of course, will interact with each other with coupling, which we have tried to decouple during the sensing period. But after I acquired some spectrum of these, some of these spins will be polarized, and so I can let them evolve under their own internal Hamiltonian and see what they see to each other. So what we can do is, if you want a 3 steps type protocol. So the first step, we will sort of polarize individual spins. And at the same time, we can acquire this type of one-dimensional spectrum. Then we can let the nuclear spin polarization diffuse into the network given by the molecule itself. And then after a short time, we can sense back where the polarization is. And this allows us to figure out what are correlation between different spins. So what you get is this type of 2D spectrum which is actually quite typical in NMR. So a second way, of course, of measuring protein structure is by using solid state NMR techniques, and they routinely measure this type of 2D maps. So what do they represent here? So here what I have is the frequency of my sensing step, while here, sorry, this is the frequency of my polarization in sensing step, so the step number 1, and this is the frequency of the second time step during which I'm sensing where the polarization is done. So along the diagonal, of course, I just have basically the projection of this 1D spectrum. So this is, I polarize the spin and then I still measure it out. But then I also start seeing some terms which appear on the off-diagonal terms, which basically where I polarize a little bit one spin, and now that polarization is sort of jumped onto a second spin, and then I measure it there. So in this way, I'm able to infer more information. And of course, I do not need to sort of measure all n square coupling between all the spins. I only need to, I already have 2 n parameters, and I need another n set of parameters, so I do not really need to reconstruct all possible coupling in order to fulfill the full structure. I added also some prior information about where we expect to have the spins, so typical, for example, typical length of bonds in proteins. This becomes quite enough to be able to really fully reconstruct the structure of the system. So as I said, this is a simulation, and hopefully we will be able to put them in practice. For the moment, we're just trying to polarize a single spin and see what gives us. Okay. So I think that I'm a bit in advance, but it's just good. And I just wanted to do a full summary of my 3 lectures. So the first lecture was really concerned about how we can control hybrid systems. And so what I told you were just some tricks on how to control this hybrid system, taking into account that often you have this strong interaction among different parts of your system itself. But I think that another important message was that you can really use one part of your hybrid system to control the second part of the other system. And that can really give you some faster, robust control, which is might not be able to achieve with a classical control. The second lecture was instead concerned about how to achieve quantum communication using this hybrid system. And really this is at the core of what hybrid systems are good at, which is to be interfaces and transducer between different modalities, different physical systems. And I also talked a little bit about how we can achieve a robust transmission of quantum information at the solid state using this chain network of qubits. For me, they're spins, but if you have a better system, feel free to replace your two-level system. And then today, what I talk to you about is how we can achieve sensing using hybrid systems. And I think that there are 2 ways in which hybrid system can be really good at this task. One is to try to achieve, again, non-destructive measurements, sort of in the same way that we can control a system without introducing noise by using a quantum system. Also, we can try to sort of measure another quantum system using, of course, using a quantum sensor in a way which might be non-destructive for this quantum demolition measurement. But a second very important way in which quantum sensor can be important is that they can really do measurements down at the nanoscale, where a lot of quantum physics happens. And so they really make it possible to measure one quantum system using another quantum sensor. So with that, I just want to finish, and this is my group back at MIT. So we are the quantum engineering group because nobody can spell my last name, so I So you finally see why there was this small logo in my slides. So it's just a keg if you like beer, and you can get more information at keg.mit.edu about the group. So if you want to join us as a postdoc, let me know. That would be interesting. So the MIT is also part of us. Okay, so thank you very much for your attention.
Yeah, thank you so much, Paola. So Paola unfortunately has to leave later this afternoon, so this is your last chance to ask her. Yeah.
So, what would you just say is the progress towards having a stationary sensor? So, one of the big goals is molecular structure, determination of proteins and things, and this is a very hard thing to do, right? So, people have imagined scanning around the sensor, or you could have a stationary sensor, and talked about strategies. How far away are we from decoding the structure of proteins in a way that's better than you can get with other things, like, for example, MRFM or just cryo-EM? Is that within sight?
So there are two things. So one is there are many ways of deciding if it's better or not. So for example, you mentioned MRFM, you need cryogenic temperature. So that might not be the best way of looking at a protein, which typically is at room temperature. They might have slightly different properties at room temperature with cryo. So even if you don't get the same sensitivity spatial resolution of MRFM, it might still be very valuable. So it's difficult to really say, okay, when is it going to be better? It depends. So also with respect to X-ray, they have a spatial resolution which are really great, but there are some particular classes of protein which they cannot really address.
I understand. So use your own definition, unconstrained, however you want to answer the question, but do you have an answer?
So the second caveat, and then I will try to answer, is that probably you do not really want to measure the full protein. So that is probably going to be very hard with this sensor because you're really sensitive to local structure. So you can sense like 5 nanometer away, let's say you're 2 nanometer below any surface with nanodiamonds of bulk, and then you can measure for 5 nanometer. But you're not going to be able to reconstruct the full protein structure, which are like 100 nanometer for the small one, mitochondria, and even more. So, and I don't think that the goal should be that, because people have fairly good ideas of what the general structure of the protein is, but maybe we do not know how binding site behaves when it's in particular condition and the presence of the ligand, etc. So that second goal, I think, is much more plausible with this type of techniques. So again, when is it going to be better? I do not know. For some tasks, I think it's going to be okay. For when are we going to achieve this type of task? I think probably like 1 year or 2, because people are doing such advances so quickly that I think it's not really feasible. I mean, I think that like a year ago it didn't seem really possible to measure a single microsphere already. So, I mean, I have a lot of faith in my colleagues. I don't know me, but my colleagues are great. They're going to do it.
Marcus.
Along these lines, because I also think that the outlook, in particular in this direction, is just so fantastic. I was really shocked 2 days ago to see that there was the last science issue, there was a recent science paper retracted actually on single proton spin detection, Christian's group. And the reason was obviously that they could not distinguish the carbon-13 influence from the carbon-13 spin from a single proton spin. So I'm wondering, the way I read it, would your answer not be, well, that if you do quantum control, then you can do that, and so it's okay again? Or how harmful is that actually what happened then?
So one has to be very careful, and we are also learning the same. So for example, we are doing this polarization, and we are also seeing a strong signal, and it was like, this is way too good to be good, to be the real thing. So, and it seems that probably that is also because of the nitrogen spin associated with the MD set. So one has to be very, very careful. And there are signals that is not, the spin that you're looking at is not going to be important. So even in Christian's case, I mean, we were discussing back in September, and it was like, well, you have, they had sort of like a weird ratio of their coupling strength to their resonance. And that seems sort of weird to be happening like that. And it's all a problem of how good in the end your control is and how well you understand how to control. So the problem was that they had finite width losses, and that was not taken into account in a perfect way at a given magnetic field. So I don't think that it's an insurmountable problem. Just like you need to know what you're doing. If like it was really a combination of selecting a particular magnetic field under which condition the carbon overlapped with the proton. If it had been like 50 Gauss away from that, where it would not have happened. So it's also bad luck in some sense. But yes, it's teaching us that you have really to be careful in what you're doing and really understanding. I guess you were saying yesterday, not only the ideal condition of the experiment, like most of the analysis you do with, you have infinite pulse, like infinite weak pulses, so very instantaneous. That's not the case. They're very, very fast, but not. And so like all these like small details away from the ideality, one is to understand. It's not a fundamental issue. Just need to know what is going on, but one has to be careful.
Paola, thank you again so much for...
Yeah, thank you.
Don't go away quite yet. For the hike, there will be a shuttle bus which will pick us up right in front of here.